Fokennek. So the floor is yours. I don't know how to. Okay.
Thank you very much for that. And I'm happy to be here. I think this is the time in this house for a presentation. And I must tell you something about the history of this presentation. Last year, I was invited to a conference in Innsbruck. It was a conference on the 100-year anniversary of a conference about aerodynamics.
So I'm sorry,
Okay.
I would like to ask you to
Be here.
Here, yes.
Okay. Yes, there was a conference on aerodynamics in 1922 in Innsbruck. And the organizer of this conference was Theodor von Karman. And so we had last year such a conference in Innsbruck to repeat something of this, but mainly this was a discussion about turbulence in the atmosphere. And then I thought when I come to Budapest, perhaps it's interesting to look why von Karman and turbulence in the atmosphere, is there a connection or isn't there a connection? Because we have some names from him for some parts in the atmosphere, but we have no meteorological papers from him. And so I want to try to take something of my presentation last year and combine this with some special things from Theodor von Karman and to look where are the connections. And we start with this nice picture. Perhaps you have seen this picture in spring this year. This is a Karman vortex street, and this is you see here the Canarian Islands. We are in the trade winds, and we see here this nice vortex streets. A wonderful thing. The only problem, Karman investigated a standing cylinder in a moving fluid, and a moving cylinder in a standing fluid. And here we have a moving fluid and standing islands. It's a little bit opposite what we are doing in meteorology. So let's start a little bit with, no, doesn't work.
Okay.
So, he was born in Budapest, studied here, got a PhD from the University of Göttingen, and was very fast a professor and director of the institute in Aachen, and always had connection to Göttingen and organized in 22 this conference in Innsbruck. And then he went to the California Institute of Technology, was still in Aachen, and in 1930 he immigrated to US because he has a Jewish background, and this was too dangerous at this time. And at the end of the Second World War, he left Caltech and had different positions and came as an, I think, as an American officer in 45 back to Göttingen. And there are some pictures when he was standing with Brandl, who was already 64 years at this time, and he organized something to bring the German knowledge in launching rockets to America, and then they developed a lot of things with NASA, and this American Army got a famous medal and died when he visited again Aachen in 1963. So, and when I looked in some aerodynamics manuals, then I found a lot of things which probably always have the name of von Karman, and I checked where is something which could be in relation with metrology. And of course, the Kármán street we know, but here, of course, I told you the cylinder was moving in the fluid. Oh, sorry, this is better. And a lot of things I do not know. It's from aerodynamics. Interesting is there are two other things. The Kármán integral equation. I will show you this equation. And interesting is probably the Kármán Polhausen parameter. I not fully understand this. It's very theoretical, but I got the feeling that this is something in relation with the Prandtl mixing length theory. And perhaps Prandtl's mixing length theory will be in 2025, approximately 100 years old. Perhaps there are some theoreticians who will check the relationship in the theory. That may be quite interesting, perhaps. Okay, and Kármán integral equation looks very interesting. And when we have a look, but first the vortex street is perhaps nice. The papers of the vortex street are already made in 1911 and 1912, and these were quite old papers. I come again back. At this time, everything is written in German, so you have to translate it. The good thing is most of these old papers are now online available, and this is quite interesting. Perhaps you can use a translator to have this in English, and in other papers which are in German, I have the translation also here on the transparencies. So this is a Kármán boundary layer momentum equation. This looks quite well known when we know the Navier-Stokes equation. This is the advection term. This is the term of the tension, and this is the pressure term. What we are missing in this equation is the tendency. This is time independent. And this is a little bit the problem. Then he generated an integral equation, and this equation which is valid for laminar boundary layer as well as time average turbulent boundary layers. So this is true in a wind tunnel where we have a big laminar boundary layer, but not true anymore in the atmosphere where we have only a very thin molecular layer. But nevertheless, it's a nice example, and this is the difference between the thinking in metrology and here in hydrodynamics. But I think Kármán worked also with very high Reynolds numbers, and here for the vortex street, this is working in high Reynolds numbers. So he was familiar with the work with high Reynolds numbers. So we see he was close to the Navier-Stokes equation, and then we come to the equation of the wind profile near a wall in the wind tunnel, and there is the paper from 1930, and he has a typical profile equation for momentum, and provides where K is a dimensionless constant that depends on the type of fluctuation mechanism or the solution of the equation. It is the only constant that is included in the theory of turbulence developed here. So this is what we know today. This is the only constant in any profile equations which we also use in the atmosphere. And this was a little bit different to Prandtl's work and Prandtl's ideas, but nevertheless, in 1933, Prandtl agreed with Kármán's theory. So we can say, okay, the typical wind profile in the atmosphere based on Karman theory, so it is okay that we call this K now the von Karman constant. I will come back what happens with the von Karman constant in the future. And this is, I think, the main point where von Karman is connected with metrology. All the papers are, of course, far away from the metrology itself. So, and now came this conference in Innsbruck in 1922. We had two organizers. The one was von Karman coming from Aachen, and one was Levi Civita coming from Rome. I hope you know him. Yes, especially his epsilon, you know, perhaps. For all who are not familiar with this, when you write the Navier-Stokes equation in the notation of Einstein, and he was also the person who made for the relativity theory the mathematical background. And in the Navier-Stokes equation with the Einstein notation, there's an epsilon, and the epsilon is sometimes 1, -1, or 0, depending on the coordinates. So you can write the Navier-Stokes equation in one equation, if not provided several equations. And this was this Civita-Levi. And you call normally this as his index or his number. So, and both organized in conference about hydrodynamics and aerodynamics. And the problem was there came scientists from many countries which were fighting against in the First World War. All these scientists were involved in the construction of airplanes and similar things, and von Karman developed a vertical starting system in this time. So it was, many of the papers are about airplanes and aerodynamics around airplanes and so on. And then I checked why the colleagues from Innsbruck want to take this as an idea to discuss about turbulence in the atmosphere. And I checked the summaries of this conference, and I found no word atmosphere in the whole summaries, only one normal atmosphere. Metrology not, or German or English not, but 40 times Reynolds, 1 time Taylor, 1 Richardson, and 1 Wilhelm Schmidt. And when I checked more into detail, then all the 3 names, Schmidt, Taylor, and Richardson, were in a paper of Ekman, and this was the only not aerodynamical paper in this conference, and it's called about the dynamical laws of the streams in the ocean in German. And he found that we have a lot of problems with the determination of the turbulent friction, but there was some success from Schmidt, Taylor, and Richardson at this time. And it's true that at this time these 3 scientists work quite a lot about this, and I will go into details what they have done. So then the only meteorologist at the conference was Bjerknes. Wilhelm Bjerknes was, up to the beginning of the First World War, the founder of the Geophysical Institute at the University of Leipzig and was their professor. He is familiar with the school of Bergen, with the polar front theory and so on, but his presentation was about forces on aircraft and nothing with metrology. And the same presentation, the similar presentation, was von Brandl at that time. So no metrology at all. And von Karman discussed again the form of the the vortex stream with cylinders in a stream, and but you see here also an stamp, but the stamp was issued, I think, on the 110th birthday of von Karman, so it's not a very old stamp, it's quite new one. Maybe new one is 30 years ago. So he discussed that as a flow, and this forms discrete vortex, and such a vortex street is as in cylinders in liquid, and this is a paper from a picture from the atmosphere. Yeah. So for many of us, the Karman vortex street is a meteorological phenomenon, but in reality, he always investigated this in the wind tunnel or in a fluid tunnel or something else. So, and I will show you the persons who are mentioned in this conference, which are related to meteorology. This is Reynolds. Okay, this is very old. It's a paper from 1895. I think this is the first paper about atmospheric turbulence, and everybody who works in this field makes citation of this paper. I do not know how often it is today, and it's online available. So you see here the Reynolds number, and you see the Reynolds decomposition, which is necessary to make from the average Navier-Stokes equation the way to the turbulent Navier-Stokes equation, or to use this part here for eddy covariance technique. So it is familiar for all who are working in the atmosphere. So Reynolds is one of our famous start in atmospheric turbulence. And then I show you something what you don't know perhaps. You know the word of turbulence element perhaps, or turbulent eddy or something else. And this word is generated by Barkov, and he told this as elements of wind turbulence. And Barkov was on the vessel Germany in Antarctica, but this came not to the Antarctica, it was fixed in the ice there, and he had 1 year time to do something. And he had the wind registration from the Potsdam Observatory and analyzes and found that there are fluctuations in the wind speed, which you see also in the wind direction, and he has written a small booklet about these turbulence elements in the wind field. And so I think this is also something about our understanding of turbulence, because we discussed we have turbulence elements, which are smaller, will be larger, and how they are mixing and so on. So this comes from Barkov. And Sir Taylor is important in this field, and Sir Taylor was important to analyze the turbulence spectra. The turbulence spectra is based on Taylor's work, and we see here his papers from 1915 and 1922. These are the important papers from him. And then it's Richardson, an important person in development. And Richardson has here the temperature, and here the wind speed, and here you see the criterion of the critical Richardson number of 0.2. These are measurements over a forest, and I would say these parts here are even something like coherent structures, which we now investigate. It's an interesting paper in detail, but from this paper comes the Richardson number as a measure for the atmospheric stability. And Then the other person is Wilhelm Schmidt from Vienna, and from him is a word which is still used in English language. This is an Austausch coefficient, or the exchange coefficient. And he says that the flux depends on the exchange coefficient and the gradient. And he says we can use a constant value which is used in the wind tunnel in a similar way also in the atmosphere. The problem of this is this works fine under neutral stratification, and under unstable and stable stratification we have to do some modification, and I will discuss this issue now for you. So, and then came the 70th birthday of Jacques, and there was a small booklet issued to his birthday, and Prandtl was asked to write a paper for this birthday. And he says he accepted the invitation to write this paper, but he has nothing to write. And so he simply used all what he is knowing in hydrodynamics and write what is the transformation to meteorology. And this is a nice paper about meteorological application of fluid mechanics in German Britain. And you can print this as an introduction to a meteorological textbook. There are also equations are wonderful there, and there he accepted also the von Karman constant with 0.4. Von Karman itself measured 0.38 and Nicorazze 0.36. About the value I will discuss later. So this was the connection between the aerodynamics in wind tunnel to the meteorology with this paper by Prandtl, and therefore we always think Prandtl has done everything for meteorology, but perhaps it is an issue for theoreticians to look in the very mathematical papers of Theodor von Karman and see what he has done that Prandtl was able to do this, because he was a long-time assistant and perhaps also friend of Prandtl. And then comes a person who is perhaps not all well known, but who are working in boundary layer should know his name. It is Heinz Lettau from Leipzig, has a PhD from Leipzig, was as assistant of Professor Weigmann, and during the Second World War, he calculated the ballistics for German rockets flying from Germany to UK. And the meteorological background for the ballistics comes from him. And it's not much written, and it doesn't tell much. It is not known. He was during D-Day in France. It's not known if he said to his general, go home during this time or not to go home. This is not exactly written, but nevertheless, he was then a prisoner, very fast a prisoner of the Americans, came to US, discussed in US, came back, was in the German Meteorological Service, and go back to US. It was at the Massachusetts Institute of Technology, and got then a professor in Madison, Wisconsin. And the interesting thing, and about this I worked, how there is often discussed the question, is he the person who developed the Obuchov length, or is Obuchov the person who developed the Obuchov length? I published a paper about this. I show you only a little bit, and this is perhaps also the idea why I say interesting to look in von Karman. There are often other works which have done similar things, and then comes a person like Prandtl, and he says, this is who, and now Prandtl was the name. And here you see this long line of persons who have done something in surface fluxes You see here Schmidt von Karman with the von Karman constant, and then we speak a little bit about Rossby and Sverdrup. This is also important persons. Then Obuchov and Lettau, Monin and Obuchov with the similarity theory. These with the length of the stability parameter, and the experimental part comes from Boschevera from Kemel to make measurements available. And then we have universal function. Here the three persons, Sienkiewicz, Bissinger, and Wingard. And finally, Ulf Höckström, who made a recommendation how to use the von Karman constant. And this is Höckström's work. And this is from my paper, but this equation is in the paper by Rossby and Montgomery. And when you look in this equation, there is a very complicated part here. And when you use this part and move everything a little bit, then you see that the gradient of the wind speed or the momentum flux is a function of Z over L. Z over L is already standing in the paper of Rossby and Montgomery. Okay, they stopped at this equation, nothing not more. But when you look in the details, you will find that Z over L is already in this paper. And with this paper and with this dependency on stratification, Rossby and Montgomery and later on Sverdrup were able to calculate the energy fluxes at the Earth, and Albrecht in Potsdam used in 1940 the Sverdrup equation and has written the first energy balance of the Earth's surface. So you see, here is something found, not interpreted, not selected, but there was the key made for the Obuchov theory. And Lettau, as well as Obuchov, knows this paper, have made the reference to this paper, so perhaps they have done similar things like I have done and to see this paper. So this is at this time, and then we look in the papers by Obuchov and by Lettau. Here you see the Obuchov Z over L, and the Richardson number found this dependency, and this is the same. You have to move by 90 degrees in the book by Lettau, and it looks as the same. He has not only isolated this, but these are the same numbers, the same picture, as he found the same dependencies. The only thing is, was that are not found the universality of the Obuchov length of L. What he found was a stability Z over L. And so my proposal is to call Z over L as the Obuchov-Lettau stability parameter, but the length and the universal idea of this length, this really comes from Obuchov and not from Lettau. And this is perhaps the solution of this problem, who was the author of which. Yes, and finally, we should come to Ulf Höckström in Uppsala. He made some verifications of all the universal functions. And there are two things which he has done. First thing is he recalculated all functions for a von Karman's constant of 0.4. You know, we discussed the size of the von Karman constant because sometimes was discussed that the von Karman constant depends on the roughness Reynolds numbers and so on. There are several papers about this. And you know that we have always in many equations in metrology in self-correlation. Yes, so when we have on the one side the friction velocity and on the other side of the equation, the universal function. And in the universal function, and is set over L, and in L is the friction velocity. So there is a certain correlation. And many of the papers analyze that self-correlation. Could be the possibility that we sometimes discuss the von Karman's constant. This is not 0.4. And the work of Ulf Högström was to unify the universal function, maybe from Silting-Kiewicz, from Büssinger and Wüngard, and so on, which we use now in this form with a constant, von Karman constant, and a well-known turbulent Prandtl number, because the Monnin-Obuchow similarity theory worked with a turbulent Prandtl number, which is 1, and now we work with a turbulent Prandtl number and have included this number into our equation. And this is still a question we discuss: have we to use the turbulent Prandtl number also for laminar heat flux, or can we use, as we separate with the Schmidt number? And this is the discussion is still ongoing. So let's look in the statistical turbulence. And we have the turbulence spectrum, and we have the discussion about isotropic turbulence. This is related to Kolmogorov. Parts are moved to temperature by Obuchow, and there are many papers by von Karman about isotropic turbulence in the beginning of the 30s. And these are hard to read, and perhaps some theoreticians look in the equation of von Karman's paper in Kolmogorov's paper, and to find out what was already known for Kolmogorov at this time and what was known from Sir Taylor at this time to discuss this issue. So I think here is, if anybody retired and is good in theory and mathematics, then it's a good job to look in von Karman's papers and see what he has done in the case of isotropic turbulence. This is not only to do something, this is probably important, because when you look in Lettau's papers, Lettau always separated between isotropic turbulence and non-isotropic turbulence, and developed this theory of the stability parameter for isotropic turbulence. And now in the discussion is, and there are some scientists in Innsbruck work about, if the problems which we have with the Monnin-Obuchow similarity theory is because the theory is only valid for isotropic turbulence and probably not for non-isotropic turbulence. So I think this is a good issue to go back in the old papers of Karman, of Taylor, of Lettau, to see, have we to separate in the atmosphere isotropic turbulence, or could we only discuss turbulence that says turbulence is frozen, and frozen turbulence over a certain distance? So I think this is an issue which we should discuss, and perhaps in relationship, is the Monnin-Obuchow theory valid, universal or not universal? This, and therefore perhaps start at this point with von Karman. Yeah, and some persons here, Bachelor is an important person who made Kolmogorov theory in 45 already popular in US. He selected a lot of Russian papers, translated it, and made it available in US. And then we have the Kolmogorov theory was also developed by Weizsäcker and Heisenberg. Yeah, a little bit later, and of course independent because of the Second World War. And then we have the local isotropy for scalars by Obuchow and by Corsin. You know perhaps the Corsin number in some spectra and so on. And Townsend make the Reynolds similarity theory, and then we have the use of the structure function, yes, which is the structure function of refraction or temperature, is an output of remote sensing techniques. And the theory for this comes from Tatarsky and from Obuchov, and Kalistratova realized the first soda, for instance. So it is all well connected, I think, and also in the last time series, these are the coherent structures. The basics came from very early. This is a Kelvin-Helmholtz instability. Oh, here is from Innsbruck the picture. And the Kelvin-Helmholtz instability is a cloud phenomena which we like as much as the Karman street. And then we have the Brunt-Wessela frequency, which is important for the stability. And then it was Deardorff who found that in convection we have counter gradients. And later on it was found that counter gradients are still in the atmosphere in the forest, and I found it in Antarctica in very stable stratification. So, and we have used that with some discussion about stable stratification. And here is the Kelvin-Helmholtz instability over canopy flow with the coherent structures, which make an important part of the exchange. So everything depends and has a history, and this I wanted to show you here a little bit. And the history you see also in our textbooks. And this is the first atmospheric turbulence by Lettau, then from Pascal the diffusion, and from low-speed aerodynamics to aeronautics from Karman. And then we have the nice books about from Monin Yaglom in two parts about statistical fluid dynamics. It was issued about 10 years ago again. It's a really fundamental and nice thing. Then we have the Dutton book, the Newstead book, then a summary book about turbulence, and the last book about atmospheric turbulence is from Weingart, and I do not know if there's a new book. I do not remember. Interesting is a book by Frisch, who analyzed the Kolmogorov theory and discussed the Kolmogorov theory. And also some books about history from Frisch, and this atmospheric turbulence. And this is a nice book with a longer chapter about Karman. And there is a little bit written about the street, but much written about the isotropic turbulence. And this is perhaps interesting. Then here is also coherent flow, and in books from me, there is about the measurements history, and here's a little bit history about micrometrology, and some parts which I discussed here are in this book. And thank you very much. And this was the question, is von Karman relevant in metrology or not? Thank you.
Thank you very much for this very interesting historical presentation. We are very proud of Karman Tobor, Hungarian origins, for sure. Do you have questions or comments? Yes, please.
I would have a short question because I'm teaching this material length is near length disturbance, and actually one of my problems is when I talk about von Karman constant 0.14 and so on. This is the value, but actually I don't know whether this constant has physical meaning. I think has physical meaning, but I don't know. It's fascinating, of course. I don't know what is the physical meaning of this concept. And it would be very nice to hear something about this dilemma.
I think the dilemma is already written in the paper by von Karman. He says this is the only dimensionless constant which we have to include in this equation. And there is not something like I can say, oh, this is a ratio of this and so on. It is a constant, like a nearly universal constant, which we have in physics somewhere else. I do not know anything. For the Obuchov length, there are some interpretations that it's a relationship between the buoyancy and the momentum, and it is related to the thickness of the surface layer in a certain way. There are some explanation for the Obuchov length, but I do not know any explanation, physical explanation for von Karman constant. And I think it is written in this paper and also in the Brandl paper, you have to use in the momentum profile the von Karman constant, which is constant and is 0.4. The problem what is important for teaching about the von Karman constant, we use the von Karman constant in different ways, especially in the papers by Silicikiewicz. He includes the von Karman constant in the Obuchov length. And this makes it sometimes difficult to check one paper with another paper. And this is perhaps a problem because it's able to do it at a different place. And be careful at this thing, you know, it's the same as with the turbulent Brandl number. Is the Brandl number a part of the equation of the profile, or is the Brandl number a part of the Obuchov length? And this is also in different papers. And I think here Höckström had made a good job to say clearly where should we use what, and he has included the turbulent Brandl number, for instance, in the universal functions. This is, but I cannot give you an idea. You must tell your students it's a constant. Okay. I have done the same.
This is a scientific question. It's of your students.
As far as I know, so this constant to me is just scaling parameter, more or less, which, as far as I know, everybody calculated by experiment using experimental data, and the values are a little bit different. So for some time, as far as I know, it was even a question that it's really a constant or not. So I think it's an open question that it has some physical meaning we don't know about, or it's really a constant with some bit of error. Yeah, so.
Yes, you can say, of course, it's a scaling between the gradient and the flux. Yeah, but
Yeah.
and the differences is also difficult because the von Karman constant and the turbulent Brandl number are standing at the same place in the equation. Yes, yeah. If there's an error in the one and the other is constant, or it's difficult. And the other problem is, of course, all differences are in the range of our errors in our measurements. Mm-hmm. Yeah? So we have no possibility to make our measurements better than and often it's given the turbulent the Karman constant with 0.4 and between 3.9 and 4.1 or something. Yeah, but this is much less than 10%, and the accuracy of our measurements is 5% or something else. So it's the same.
Yes.
Now, at this moment, I was inspired for the second version. All these things what we heard is the theory of turbulence. The question is this theory of turbulence universal for other planets? Is valid or not? Or it is Earth specific?
This is a very difficult question. I think when the physics is universal specific, then also the turbulence is universal specific. We do not have, I think, other physics on another galaxy than on our galaxy. And the interesting thing, and I told you this in one book, Coherent Structures in the Earth System, these structures are in the atmosphere, they are in the water, and they are in the inner part of the Earth. Always we have the same structures, only the typical numbers, like the Reynolds numbers and so on, are different. And when the scaling numbers are in the same relation, we have the same structures. And so it is the structure may be different in a different part of the galaxies, but when we normalize that with the similarity numbers, then it should be similar. I do not believe that the physics or chemistry is somewhere else different. Only the distribution of the elements.
Other questions? Well, if not, I would like to thank you again for this presentation and also for the visit.
Thank you.
It was very nice meeting you. Thank you so much.
Thank you. So, this switch off.
Yeah. Köszönjük szépen az online térben lévőknek is. Viszontlátásra.